and that his while Professor Joshi, who was of course with his PhD with Professor Sharma. Pandit has been to Cambridge. He's also got quite a few awards in his CV. But the only thing I want to say, which is extremely good, especially to students, is that he got Professor Ariva Didaksha Best Teacher Award on 15 occasions in the past 20 years. Please remember, these awards are given by the students. So I don't want to stand between you and the best teacher. So let me request Professor Pandit to take his 35 minutes on design strategy for industrial crystallizer. Professor Pandit.
Thank you. Yeah. And Mike has made my job quite easier because he has identified the basic processes which are involved in the industrial practice of crystallization. And I'm going to actually talk and discuss how these practices can be implemented and what are the design parameters which you need to take into account while designing an industrial crystallizer. So basically, any crystallization process, as you would understand, Mike has elaborated the role of metastable zone and how to be able to get a controlled size distribution of crystals, how one needs to operate within the realm of metastable region so that you do not get uncontrolled nucleation and you are in a position to control the crystal size distribution, which ultimately is a desirable property for the product which you are trying to make. Basically, we start again with the same graph. So I have shown it as a linear graph, need not be linear, but this is essentially a solubility curve. And there are two methods in which the crystallization is carried out. First is a cooling crystallizer. So you are on this side, which is unsaturated liquid with solute dissolved in the solvent, and you can cool that particular material, and cooling brings this particular system on the left hand side of the solubility curve. I have not purposely marked the metastable region in here, which we will discuss in my second lecture, but here essentially cooling results into supersaturation. Now this supersaturation is supposed to precipitate out. How it precipitates out, in what form, whether it is in the form of powder or nuclei or crystal growth, is a different story. We will discuss it later. But the difference between the saturation solubility point and the actual conditions is the quantum of solute which is going to precipitate out. Alternatively, you can evaporate part of the solvent so that the system becomes again supersaturated, and as you can find it from here, that the quantum of crystals which are going to crystallize out, or the solute which is going to crystallize out, is likely to be significantly higher. However, evaporative crystallization needs to be accompanied by cooling, followed by cooling, for you to get higher recoveries. Just evaporation, because your mother liquor is at a higher temperature, it will have a higher solubility. You will not be able to recover the same quantum of product if you do not cool it. So just evaporation is rarely practiced, but evaporation followed by cooling is the system which is operated to get enhanced recovery of the solute material. So the typical crystallization operation can be simply expressed in terms of you have a solution which is fed to a crystallizer, you supply heat, and either you operate it in a batch mode after sufficient quantity of solvent is evaporated, or the temperature has reached, so you get a slurry mass and the slurry is taken out, and then you carry out your subsequent operations of filtration and drying, which is desirable for the sale of this particular product. So if you look at the different types of crystallizers, broadly speaking, there are three types of crystallizers or four types of crystallizers which are operated in an industry, and you can have multiple modifications in it, and I'm going to talk about what sort of modifications are required for you to address the specific parameters which are responsible for you to get enhanced recovery of the solute, as well as whatever solute which you are going to get is in the desired crystal size distribution form. Right, so you have batch crystallizers, you have continuous crystallizers, you have classification based supersaturation by cooling alone, supersaturation by adiabatic evaporation and cooling, so on and so forth. So these are the operations which are necessarily practiced or operations which are implemented in any operation of crystallizer. As discussed in the morning in the first lecture, essentially you need to create a supersaturation and then allow that supersaturation to get desupersaturated in the form of deposition of the solute molecules on either already existing crystals which are in the form of nuclei or added seeds which are going to provide the phase for the deposition of the solute. So this is a typical agitated crystallizer, and you can imagine this is the standard crystallizer which is operated in most of the crystallizer operations, and you can find what are the requirements in here. You have an agitation. Why agitation? To keep the solids in suspension so that all the surfaces of the crystals are available for the deposition of the solute. The rate of growth of every surface will depend upon thermodynamics, as was pointed out, and the crystal will not necessarily grow in the form in which we want, and we will talk about that a bit later. You require material to be kept in suspension, and crystallization process as such is exothermic. So you need to have a mechanism by which you can remove the heat when you want to carry out a cooling type of a crystallizer. When you want to carry out evaporative type of crystallizer, you are necessarily required to supply the latent heat of evaporation of the solvent. So basically heat transfer is going to be a criteria as far as design of crystallizer is concerned. So you can operate it in a batch mode or operate it in a continuous mode, as long as you are able to provide the required residence time to adequately supply the necessary heat flux required for either evaporation or cooling. You will be in a position to get the material precipitating out, not necessarily in the form in which you want. That means not necessarily controlling the crystal size distribution. To control the crystal size distribution, you need, and usually you do adopt a specific rate of cooling similar to specific rate of evaporation, and this can also be understood, modeled, and equations are available. We should talk about it in due course of time. So bypassing the cooling through cooling coil, the mass in the crystallizers cools. So essentially any crystallizer will require material or a mechanism by which you can keep the solids particles in suspension to offering all the surfaces for the deposition of the solute. And a second mechanism is to transfer heat to the material which is inside, either remove heat or supply heat depending upon whether it is cooling type of a crystallizer or evaporative type of a crystallizer. Another design which is quite popularly used, which is a Swenson-Walker type of a crystallizer. It's a horizontal cup where material enters from one end, and you can have broken jackets, and each jacket can be controlled to a different temperature levels to get the rate of cooling which you require to achieve a specific size distribution for the solute which is crystallizing up. These are the typical numbers, and you can refer to this. These slides are available with you. Third type is essentially an Oslo type of a crystallizer. Here, this is also called as an ideal classified bed crystallizer. What happens is, you take the material from in here, and then you pass it through a cooler, a heat exchanger. You take out the heat associated with it, so you create the degree of supersaturation, and this material is then reintroduced, creating a liquid flow pattern. Now this liquid flow pattern will essentially segregate the crystals. Smaller size crystals will occupy the upper location, and larger size crystals, because of their higher settling velocity, will take up the lower position. So if you keep on taking out material from the bottom, essentially you will be collecting larger size crystals. The smaller size crystals are likely to get recirculated. They will be exposed to supersaturation again. In the process, they will grow and then keep on taking up lower and lower and lower position after each circulation through a cooling zone, and essentially you will get layers of crystal sizes, starting from the smallest crystal size in the upper layer and the largest crystal size in the lowermost layer, and depending upon what crystal sizes you want, you can collect the material and get the crystal size distribution as you want. Third method which is used is a vacuum crystallizer. Since the process of crystallization is exothermic, the heat is liberated. Now this heat itself can be utilized for the evaporation of part of the solvent by applying vacuum. Applying vacuum will evaporate certain solvent. Evaporation of solvent will allow more crystals to precipitate out. More crystals precipitating will result into release of more heat. Again you increase the level of vacuum and the process can be continued. And this controlled vacuum, depending upon the heat of crystallization associated for a system, you can effectively exploit to get the crystal size distribution which you want. So if you look at all this, you consider the fundamental issues in any design of crystallizer. These fundamental issues are solid suspension and agitation mechanism required. Second is near wall solid particles can get accumulated because you have a surface which is either cooled or it is hot. If it is cooled, then the maximum supersaturation is going to be created on the cold surface. So the first deposition will take place on that cold surface itself. The deposition of the material on the cold surface will severely hinder the heat transfer coefficient. So you require some mechanism by which to keep that particular heat transfer surface clean by some sort of a scraping mechanism. So near wall solid particles can accumulate and you need to keep on cleaning up this heat transfer surface so that you can keep on getting the required heat transfer, either supply or removal of heat. Vaporization of solvent, cooling, heat transfer mechanism leads to gas generation. Now this is an interesting issue. You design something to keep the solids particles in suspension and then something is getting evaporated. Now when you evaporate it, vapor bubbles are going to get formed. So the system transforms itself from a solid liquid system to gas liquid solid system. As a result of which the impeller power consumption significantly changes. So whatever impeller speed which you had chosen to keep the solid particles in suspension, you may have to increase that particular impeller speed because the density of your mixture is lower due to the presence of vapor. So it is likely to change the entire flow pattern significantly, and if that is not taken into account, you will find if more vaporization is allowed to take place, these vapor bubbles keep occupying the solid mass, then this may result into a significant reduction in the power supplied to the system. That will reduce the velocities. That reduction in the velocities will reduce the heat transfer coefficient. That will reduce the heat transfer capability. As a result of many complications can arise. So you need to handle this gas liquid solid systems and arrive at appropriate impeller type and impeller operating speed so that the system is capable of taking care of this vapor which is getting formed. Ultimately, when you are able to achieve all these three, the resultant product has to have a specific size distribution. So depending upon the time available, we will talk about how the crystal size distribution can be obtained. If not in this lecture, in next lecture, we will definitely talk about that. So let us focus our attention to solid suspension. And as chemical engineers, you know solid suspension can be achieved if you create forces in the upward direction which overcome the forces which are related to buoyancy and drag forces and the gravitational forces which is going to make the particle settle. So that gives you a simple correlation depending upon, of course, the Reynolds number of the particles. You have three different correlations available to estimate the terminal settling velocity of the solid particle. This just gives you a sort of a tutorial. If it is in the creeping flow regime, this is the equation which you use to estimate the settling velocity of the particle. In this intermediate regime, you get this. In the turbulent regime, you get a different flow, equation. Now, why this is required? So, when the nuclei are getting formed, their nuclei may be in this particular regime, in the laminar regime or a creeping flow regime. But as they grow, so you will find that keeping suspension of nuclei is relatively easy. But as they keep on growing, their settling velocity is going to increase. And if you do not take into account this increased settling velocity, you will find as the larger particles get formed or the crystals grow, these particles will tend to settle and you will get a completely different crystal size distribution than what you desire. So this is a typical example. I need not spend time on it. It tells you how the terminal settling velocity can be estimated. Based on the terminal settling velocity, how you can estimate the Reynolds number. Once you know the Reynolds number, you know which of the equation is going to give you the correct value of the, it is the iterative calculation which you need to do to arrive at the terminal settling velocity. To be able to achieve this, which is suspension and heat transfer, you have to use some impeller, some agitator. And what choices do you have? You have choices in terms of diameter of the impeller to tank diameter, vessel diameter ratio, the direction of the flow which is created due to the impeller action, the kind of shear, if you want to de-agglomerate the crystals, if crystals have a tendency to agglomerate and form larger crystals, not because of growth, but only because of agglomeration, then you need to create a fluid shear so that this de-agglomeration takes place and you get the original crystal size distribution. So you have open impellers, you have closed impellers, you have radial impellers, axial impellers, high shear impellers, high flow impellers or low shear impellers, which are typically different types of designs. I'll show you some designs which are currently used. These are radial flow impellers, open impellers, effectively operate with lower D by T ratio. Now this is a qualitative description. When I say lower D by T ratio, typically the ratio of D by T is 0.3 to 0.4. Right? They are operating at high velocities, so it is extremely good for heat transfer. It is extremely good for the dispersion of gas, but need not be appropriate in terms of its power consumption, and we'll talk about how and what implications this power consumption has on the overall cost of the process. It is not necessarily good for solid suspension. So disk turbine, pitch blade turbine, this is disk turbine, this is pitch blade turbine, are the typical radial flow impellers which you can use. These are the other types of impellers which are used, anchor impellers or helical ribbon screw type of impellers. Now this is typically most commonly used impeller in the industry. The simple reason for that is when you start the process of crystallization, the liquid level is up to here. When you carry out evaporation, the liquid level reduces. If you happen to have an impeller located out here, and if the liquid level goes below that, what do? You can't do anything. As a result of when you compromise, this is probably the worst kind of an impeller which you can use ever. Right? Never use this. If at all you are forced to use it, I would suggest just simply add 2 horizontal plates in here, so that in addition to, this is extremely useful. Why it is useful? Because if you are using a jacket to control the temperature, then the material will get deposited on the wall, and the speeds with which this anchor will move will essentially scrape and keep cleaning the surface. So it's extremely good from that point of view, but extremely poor in terms of suspension. So the suspension can be achieved by using 2 horizontal plates, maybe inclined plates, so you can use a combination of a pitch blade turbine and an anchor to effectively remove the bottlenecks associated with only anchor. Now this is too much of metal going in it. Again, pharmaceutical industries are not comfortable with, because this has to be SS316 or SS316L. So the cost of this particular impeller is going to be extremely high, extremely good, but this can only be required if you are handling materials with the slurry viscosities in excess of 5000 centipoise. Anything below that, simple agitator using pitch blade turbine, maybe with a slightly higher D by T ratio, is more than adequate. These are again radial flow impellers, disk turbine, curved blade turbine, paddles. This is the kind of a flow pattern which it gets developed. If you use axial flow impeller, which are typically propeller or hydrofoils, hydrofoils are extremely good, very similar to the design which I showed you about ideal classified bed crystallizer. The pumps which are used for the circulation through a heat exchanger are very rarely centrifugal pumps, mainly because centrifugal pumps create significant shear, and this shear can break the crystals, and as a result of which you may get significant quantum of fines. As a result of which you use axial flow impellers, which create a very high flow but very low shear, as a result of which the crystals are protected and you are in a position to achieve, because of the high velocities, a reasonable value of heat transfer coefficient as is the requirement. So you get this, so this is the axial flow impeller which creates a single circulatory flow pattern, and then you need to estimate the power which I am going to utilize So this is the power number, density, operating speed, diameter. This is the flow number. This is a kind of a liquid flow which is getting generated, the overall agitation which is provided, and the power dissipation can be calculated per unit mass, because usually this is the scale-up criteria which is used by the industry most popularly. Power dissipation per unit mass. You have carried out these particular experiments in a lab scale. Everything else has scaled up, but you haven't scaled up the size of your particles. The size of the particles which you are going to get and use in the lab and the size of the particles which you are going to get in an industry are going to be exactly same. So, however, you have increased the size of the vessel, you have increased the size of the impeller, you have increased the RPM of the impeller to match it. Actually, it is not going to be required because you are not scaling up the sizes of the particles. So you will find with the increase in the scale up of crystallizer, in fact the amount of energy which is required to keep the solid particles in suspension significantly reduces when you scale it up. Usually people are afraid of that, but they need not be. Right, so this is how you estimate the power number. You have a laminar regime and you have a turbulent regime, and every impeller or agitator which you choose essentially has the capability of addressing a specific value of power number which can be utilized for the estimation of power dissipation. So this is typical power dissipation. So you can see if you are operating the system, one typical case, we are talking about few lakhs per annum of just the energy associated with the agitation of the power. So the choice of an impeller, operating speed, choice of impeller power number are going to make a big difference as far as your operating expenses are concerned. So typical blending operation, why blending operation? When you add a seed or you are introducing the material back after cooling it, you want this particular material which is supersaturated to get thoroughly mixed with the system as quickly as possible. Because you don't want differential concentration gradients present within the reactors. Because if those differential concentration gradients are present, in some locations crystals will grow at a higher rate, at some locations they will grow at a lower rate. And then the resultant crystal size distribution will be very broad and very wide, and that may not meet the specifications which you have. So this can be calculated by actually imagining this. You have added the material, it is spreading, and then you can estimate this by actually measuring a mixing time, which can be correlated by using what is known as a dimensionless mixing time, n into theta, theta being mixing time and n being the impeller speed per second. So mixing time in seconds, impeller speed per second, it becomes a dimensionless mixing time, and this dimensionless mixing time could be a good scale-up parameter when you want to duplicate the systems which you have studied in a lab scale to an industrial scale. Again, you can calculate this values in terms of how theta mix can be estimated. So I am not going to spend time on it, but I am available today, tomorrow. If you have any queries related to these calculations, feel free. I will be more than happy to answer your questions. But typically, for most of the crystallizer operations, the ranges of power dissipation per unit volume which you use ranges from about 0.5 to 1, 1.5 or 2 at the most kilowatts per meter cube. So you can easily use, depending upon the size of your crystallizer, what sort of motor power is going to be required, or what is the specifications of the motor which you are going to get. So when the solid suspension occurs, depending upon the type of impeller which you use, if you see the impeller action, it creates a sort of a pattern at the bottom where it forms a hump, and you keep on increasing the impeller speed, the size of this hump reduces, the particles get suspended, and finally at a critical impeller speed for the solid suspension, all the particles are in suspended form. Now, is it necessary for you to distribute these particles uniformly through the in the entire mass? What is your take on this? Is it necessary to uniformly distribute it or not? Yes, not necessary. If it is a batch operation, anyway, whether you have a solid particle suspended here or here, it is still exposing the entire surface area for the deposition. And since the liquid is getting mixed at a much faster rate, you will have exactly the same growth rate for a particle which is located here as compared to particle which is located here. The problem will come when the location for discharge of your material is situated inappropriately. if you can locate the discharge somewhere from here, let's say, and it is not uniformly distributed, then you may be selectively taking out final particles, which may not be the required case. However, if your objective is batch-wise and if your objective is to keep the solid particles in suspension, because the amount of energy which is required for you to suspend and amount of energy which is required for you to distribute it uniformly, there is a difference of 3 times. You need to supply 3 times additional energy when you want to distribute it uniformly as compared to just suspension. Just suspension is good enough when you want to have an exposure of the entire surface area for the particle growth uniformly. Exactly reverse situation occurs when you use an axial flow impeller. You get dead ends at this. Now there have been very clever designs where the bottoms of these particular crystallizers have been punched out in such a way that these dead zones are avoided. As a result of which you don't see any dead mass accumulated in these corners. Increasing impeller speed ultimately makes the particle suspension complete. And if you look at it, depending upon the type of impeller, this is the power which is required. If I use an upflow impeller, intuitively if I am interested in suspending the solid particles, so I will use an upflow impeller. As compared to downflow impeller, you will find downflow impeller uses significantly less power. So it's like this, I have got a fan out here. Right? I am sitting out here. If I have a fan directed towards the wall rather than directly impinging on me, by the time that fan changes, the air coming from the fan changes its direction, half of its velocity head is lost. So I need to operate that fan at a much higher speed as compared to the fan which is located just on top of my head. Operate it at a much lower speed. Constant varies, which is a function of geometry, size, type of the impeller, location of the impeller, so on and so forth, and lot of data is available on this. Different types of equipments can also be used. So how do we handle the near wall solid particles can accumulate? Indeed, we need to have a computational fluid dynamics essentially to be able to address this particular issue. And this is, you imagine a fluid element. The fluid element is exploded out here. Some liquid is going in, some liquid is going out. It has certain solid particle suspension in it. I can solve these Navier-Stokes equation for total mass, for total momentum in 3 directions, and the turbulence parameters, which are ultimately going to decide the solid liquid mass transfer coefficient, which in turn decides the growth rate of the nuclei which are present in it. So I can generate a sort of a flow pattern, and this flow pattern, very similar to what Gauti was talking about, that you can digitally design it. Now this is a digital design of the impeller. You need not carry out experiments. You can do these experiments on a computer and decide which particular flow pattern or which particular type of impeller is going to be ideally suited for the kind of application which you have in mind. Right, so this is again a typical case study which I have indicated out here, where what is the impeller speed which is required, impeller width which is required, the pitch which is going to be required, and you can calculate what is going to be the power number or power consumption for the type of design which you have finally zoned into. Vaporization of solvent leads to gas generation, and what happens is, imagine this is the situation. As I said, because of the vaporization, I need to do a vapor balance, essentially a mass balance. So the quantum of solvent which is present in the form of vapor and quantum of solvent which is present in the form of liquid. Because the solute has to be suspended in the liquid. If the quantum of solvent is evaporated to such an extent, there is not enough sufficient solvent available for me, it will be basically a big lump of solid crystallized mass which I will not be able to agitate. Right, so I need to have a control, and that can only be done by understanding what is the heat transfer coefficient which I am going to get, and I can do mass balance and enthalpy balance. Solute is going to precipitate out. Now this is going to be an iterative solution, so there is no direct. You need to decide what quantum of solid mass I need to precipitate out, what quantum of vapors I need to generate by evaporating the required quantum of solvent. So usually this is your circulation curve or solubility curve or the equilibrium curve. You tend to operate it in a stage-wise manner. Now the stage-wise manner, which is very similar to the initial graph which I had showed you, starting from unsaturated liquid, either you evaporate it or cool it. It is sort of a step. Now this is a step. You allow a certain quantity of material at a constant temperature, evaporate the solvent, then allow the material to crystallize out, evaporate some more solvent, allow the material to crystallize out, and you can keep on doing this. But you can imagine now this is stage wise. When it is stage wise, what is the utility? The stage wise is important because this will allow you to operate in that metastable region. If I continuously keep on evaporating it and reach it to this particular level, I will not be in a position to get the required nucleation rate, required growth rate, because I am having or crossing that metastable zone width limit, as a result of which spontaneous nucleation is expected. So particle size distribution, as a result of which, this is that case which I showed you about, that this is the way it is operated. You can get a particle size distribution. Now this particle size distribution can be expressed in the weight percent and the size of the particles. Now these are essentially all fines. Now you can consider these fines have a very small weight percent, and then this is the material, and this information in principle can be utilized to understand the crystallization kinetics. So I'm going to take another 5 minutes. I think that is what is right. So either I can present it in a weight fraction, or I can give it in the form of a cumulative weight fraction. Right? This is the same graph indicated in the form of, what was this? Linear? Linear. What do I have here? Log scale. Right? Versus average size. Very similar to log scale versus temperature. I can have log scale versus size, and I can decide various bins. The slope of this is extremely useful, as I will show it to you in a minute. And this slope can be utilized to estimate the crystallization kinetics, nucleation as well as growth. So typically, when we are interested in precipitating out a certain quantity of solute, we are not happy when we precipitate out X quantity of solute. We want that X quantity of solute to be present in a specific size distribution. That means we need to understand how each particle has grown, and this can be handled by what is known as population balance equation. So the details of which we will be talking about it in the next lecture. But here I am just giving you a brief of what is population balance equation. The population balance, as indicated out here, is you use a specific size interval, and you say that in this delta L size interval, I have X number of crystals or N1 number of crystals. So if I take a summation of this or integrate it over the entire size range, I have essentially accounted for every particle which is present in it, and that every particles when accumulated and added in terms of its weight or mass would give me the total weight of the solute which I am planning to precipitate out. Right? So these equations give me essentially a type of a curve, and these are the parameters. L is the size of the crystal, G is the growth rate of the crystals. Now this is done only for a linear growth of the crystals, as we will see that it need not be limited or restricted to linear growth. You can use 2-dimensional growth, 3-dimensional growth, so on and so forth, and we will see that in detail. So this is the kind of a graph which I had showed you about. You have obtained this particular graph. Now if the same graph can be extended and I extrapolate it for practically zero size. Practically zero size means what? Nuclei. Right? They have just spontaneously come out in the solid form. Now this N naught, as a function, if I can get different states, I can estimate the nucleation rate. Nucleation rate and growth rate, as was pointed out by Mike, is going to be proportional to supersaturation. So the degree of supersaturation will decide the nucleation rate as well as growth rate. So you can get this information by conducting simple experiments, and we'll see this in detail. So basically, the rate at which the number of nuclei are precipitating out or nucleating out is proportional to some proportionality constant, the degree of supersaturation which is responsible for it, and then it is also deciding the growth. So growth is expressed in terms of change in the length as a function of time, again a second proportionality constant, and the dependence on supersaturation for both these phenomena, nucleation and growth, need not be the same exponent. They can be completely different exponent, will be decided by the type of system which you are going to handle. But by conducting simple laboratory experiments, you can do these rearrangements and can get the estimate of the exponents m and n, as I have pointed out here. So laboratory experiments are required for the determination of constants in the above equation, and hence the growth rate and nucleation rate kinetics can be found out. So now there are two stages. Let us say, as Mike said, that 90% of the people do not have the solubility curve itself. I would say even if 90% of the people have solubility curve, they have never experimented with the solubility curve and obtained or have made an attempt to obtain nucleation and growth kinetics. If we have a solubility curve, if we have the nucleation and growth kinetics with exponents m and n, we have all the necessary information needed for the proper design of a crystalline. I'm just going to run through multiple slides with lots of correlations. You can go through these particular correlations, how each of these different applications for MSNPR can be handled, or this is all from standard textbook. So I'm not going to elaborate on that, but if you have any questions, you are welcome to put that to me, and then depending upon the different, you calculate different moments of distribution, and with moments of distribution will tell you total growth, total increase in the length, increase in the area, increase in the volume or mass, and all this can then be integrated effectively to have a crystal size distribution and also the quantum of crystals which you are going to get. So mass recovery on one hand and the recovery in the form of crystal size distribution on other hand, both these objectives are effectively met. If we start with knowledge of solubility curve, knowledge of nucleation rate, and knowledge of growth rate. Now this is system dependent, and I'm sure Mike is going to talk about how thermodynamically some predictions can be made, which could be a guideline for you to plan experiments rather than doing experiments in dark or randomly and then hoping for the best. I think I'll stop here, and if you have any more questions, we can discuss it later. Thank you.